So here in this diagram, we have this battery which is connected to the galvanometer, which is further connected to rheostat, and that rheostat through this wire, through this conductor, is connected with the coil. So this coil is actually the conductor, which is arranged in a specific shape in a circular form. We call that as a coil. Okay, so if we provide the DC to this conductor, due to the voltage, okay, which is provided by the battery, the EMF, the electric field will develop inside that conductor. That due to that electric field, the force F will be exerted on each and every free electron present inside the conductor, due to which that free electron will start motion, and due to the motion, the change in electric field, which leads to the magnetic field. Okay, so around this conductor, the magnetic field will be present, and the direction of that magnetic field is given by the right hand rule. And here in the coil, we have that same current carrying conductor, and we arrange that in a specific circular form. Okay, so this conductor, which form the one turn of the coil, will have some magnetic field, and similarly the other turn of the coil will have some magnetic field, and similarly the all turns of the coil will have magnetic field. And due to the arrangement of the coil in this specific shape, the arrangement of the conductors in this specific shape, the magnetic field will be added up, okay, inside this coil, and due to which the overall magnetic field will be produced around this coil. Okay, so if we provide the battery to this coil, okay, battery is actually a DC, and if we provide the battery to this coil, the one side of now this coil will behave as a solenoid. The one side of this solenoid will be the north, and the other side of this solenoid will be the south. Now, if we change the magnitude of this the magnitude of the current which is provided to this coil while using this rheostat, that magnetic field which is produced from this coil will be changed. The magnitude of that magnetic field will be changed. Okay, so the change in the strength of the magnetic field with the area we call the flux. So in the other word, we can say that if we provide the DC to this coil, and if we change their magnitude while using rheostat, the magnetic flux will be changed. Okay, so if this magnetic flux which is produced by this coil is changing, so this magnetic flux again interact with the same coil. Okay, then according to Faraday law of electromagnetic induction, the change in magnetic flux will leads to the electromotive force. Okay, so the EMF will be induced due to that change in magnetic flux with this same coil. The EMF will be induced inside this coil, and we call that as a self-induced EMF. Okay, this is called the self-induced because that EMF, because that change in magnetic flux is produced by this same coil. Okay, and that change in magnetic flux again produce the EMF in the same coil. So that induced EMF due to change in this magnetic flux is called the self-induced EMF. Okay, and now that the EMF induced here in this coil due to the change in the magnitude of the magnetic flux, okay, that self-induced EMF will be oppose the current which is provided by this battery, so it will decrease that current. This opposition is discussed by the Lenz's law. Now, what will happen if we provide AC here instead of this DC? Okay, In that case, as we know that in AC, the polarity, the terminal, mean the positive and the negative terminal, will be changes about 50 times in a second. In most countries, the frequency of the alternating current is 50 uh, per second. Okay, it means that the current, the AC current is changing their polarity 50 times in second. Okay, so if that change occur in the polarity, and if we provide that alternating current to this coil, the change will be occur in the direction of that current which is passing through this coil uh, 50 times in a second. It means that the polarity of this magnetic field which is produced due to a change in the current will be changed 50 times in a second. In other words, we can say that this side of the magnetic field, okay, this side of the coil, this side of the coil will be the north, and again this will be the south, and again this will be the north, and this process will be occur 50 times in a second. Okay, the change in the change in the direction of this magnetic field will be occurred 50 times in a second. Okay, so, due to the change in the direction of the magnetic field, the change in magnetic flux will be occur, and that change in magnetic flux again interact with the same coil, and due to their change, due to their interaction, the EMF will be induced inside this coil, and we call that as a self-induced EMF. That self-induced EMF is produced due to a change in magnitude and the R, the direction of the magnetic flux, and that linking with the same coil. Okay, so the EMF is induced here in this coil, and we call that as a self-induced EMF. And that self-induced EMF again here depend upon the change in the current, the change in magnitude or the direction of the current, and time del t. Okay, so this self-induced EMF is directly proportional to this. And here, instead of this proportionality sign, we will use the equality and constant. So here this induced EMF is equal to constant, and this del I by del t. So here, instead of this constant, we will put L, and so here in this constant we put this L del I by del t. Here this L is called the self-inductance. Self uh, inductance, or the inductance of the coil. Inductance inductance of this coil. Okay, so this self-inductance inductance of the coil depend upon the many factors. Okay, and I will discuss that in the last part of this video. So this is equation 1, and similarly the EMF induced is given by Faraday law of electromagnetic induction, which is equal to N del phi by del t. Okay, this is the equation 2. And here from the left side of equation 1 and the left side of the equation 2 is the same. So therefore the right side of the equation 1 and equation 2 will also be the same. Okay, so this the right side of equation 1 is L del I by del t, which is equal to the right side of equation 2, which is N del phi by del t. Okay, So here uh, this del by del t and this del by del t will be cancel out, and this will become L I, which is equal to N, and flux, the magnetic flux. Okay, so from here the inductance of the coil is given by this, okay, which is given by N phi divided by I, the current. Okay, so this is the equation for the self inductance or the inductance of the coil. Now, what is the unit of the self inductance? Okay, so the unit of the self inductance here, the unit of the self inductance is called the Henry. Henry is the unit of the self inductance, and which is given by this H. And 1 Henry is equal to, if we put this electromotive force as 1 volt, and the change in the current divided by the t is 1 ampere per second, then the inductance of the coil will be called 1 Henry. Okay, so 1 Henry is this. If we put this electromotive force is 1 volt, and 1 volt, and if we put this del I by del T is 1 ampere per 1 second. Okay, then the inductance of the coil in this situation is called 1 Henry. That is called the Henry. These are the factors which affect the inductance of the coil. As we discussed in the theory of the inductor, that inductor is a coil, and if we change the current flowing in that coil, the magnetic flux will be changed, and that change in magnetic flux will induce the EMF in the same coil, and we call that as self-induced EMF. Okay, so here is this inductance. Okay, this is actually the charger. This is actually the charger, and inside the charger we have these like shape. Okay, shapes. Okay, this is actually the inductor. Okay, and this is also the inductor, and the device in which the self-induced EMF process is occur called the inductance. Okay, inductor. Okay, so this is actually the inductor. Similarly, this is the inductor, and this is also the inductor. This is also the inductor. Now here different type of the different inductors are present in this charger. Okay, now the shape of the inductor is depend upon the inductance of the coil. Okay, so here we have this coil. This coil will have different inductance, and then this coil, and similarly this coil will have different inductance, because these three are different, they're having different shapes. And similarly the number of the turns, if we increase the number of the turns in this inductors, the change in magnetic flux will be more, and due to which the inductance of that inductor will be more. Okay, so here this inductor have more number of turns, therefore their inductance is more than this, and similarly their inductance is the inductance of this inductor is more than this. Okay, and the second factor of the inductance of the coil depend upon the material of the core. So inside this coil we have this material. Okay, this green color material, we call this as a core, and mostly in more inductor these are ferromagnetic material, and we use this because the ferromagnetic material is support the magnetic field. okay, support the change in magnetic field, and due to which more self-induced EMF will be produced, which oppose the more current. Okay, so the material used in that coil also change the inductance of the coil. And similarly, the coil area, if we increase the coil area, if we increase the area of the coil, their inductance will be more. And if we increase the length of that wire which form the coil, their inductance will be also increased. The inductance of the material depend upon these factors, and we saw that here.